Back to the lecture series on circuits and networks. This is the 16th lecture of this series, and this is just the continuation of lecture 15. So if you didn't watch the last lecture, please watch that last lecture. Then it will be somewhat smooth for you to understand the concepts of this lecture. So actually we were discussing about the transient circuits with the inductor. In last class we were considering pure inductor. Practically a pure inductor will not be existing. In any inductor, you take inductor manufactured by any company, there will be a small resistance also. So while coming to the practical scenario, we have to discuss about RL circuit. RL means inductor with some resistance, RL. That is the practical case. But theoretically, we will be also discussing about pure inductor case. In last class, we discussed pure inductor case. We can just go to those slides for recapping the lectures, the contents of last class before going to today's topics. Okay. So this was the content of last class. Inductor current equation. That is, we all know that inductor voltage equation is V is equal to L di by dt. So current equation is 1 by L integral V dt. So this is the meaning. For getting the current in an inductor, we have to integrate the voltage with respect to time. That is the case. So if we are thinking about an inductor, pure inductor connected to a DC supply, its current equation will be 1 by L integral 0 to t V dt. Actually, I0 will be there, initial current. From minus infinity to 0, it is I0. And after that, from 0 to t, it is 1 by L integral 0 to t V dt. Okay. So, we know that I0 is 0 because the switch was open earlier. I0 is 0. So, you will get I of t is equal to V by L into t. If you are completing the integration, you will get I of t is equal to V by L into t. That means the slope of the current is V by L and that is going towards infinity. So, if a DC inductor is connected directly across a DC supply, pure inductor is connected directly across a DC supply, what happens? The current will ramp to infinity with a constant slope of V by L. And we know that if you are just permitting to ramp up the current, what happens? Definitely the inductor will get burned out at some stage. At some time the current will become the rated current, and after that again if you are permitting to increase the current beyond that, definitely the inductor will burn out. So that for that we have to limit the current by some mechanism at the I rated. This is the I rated. This is the I rated. So you have to find the T safe corresponding to I rated, and from the T safe you have to do something for preventing the increase in the current. Okay. For that you did this circuit. In this circuit, initially you are connecting it to position A. Position A means you are doing a 10 volt inductor is connected to a 10 volt DC source is connected to a inductor of 2 Henry. Okay, and finally you will get I is equal to 5t. That means here also the current is ramping with a constant slope of 5. So suppose 5 is the rated current of this inductor, you will get its time safe, T safe is 1 second. So at 1 second you should move the switch to position B. You should move the switch to position B so that you will get a short circuit in position B. And then the current will become constant because you can check the KVL, and in KVL you will get that I will be constant at the position 2, and then the current will be constant at 5 ampere, and energy you will get 25 joule, that is the energy stored. So up to this we have discussed in the last class very clearly. So if anyone is facing any difficulty on this, please stop watching this video now and go back to the 15th video lecture, and then you will be very clear about these concepts. Then only I am inviting you to the today's topic, that is RL circuit. Okay, now we can start RL circuit. So this is the actual content of today's video. an RL circuit connected with DC voltage. An RL circuit connected with DC voltage. So you can see here we are having a switch. Up to the time of t is equal to 0, the switch is open. And when t becomes 0, you can see the arrow mark. The arrow mark indicates that at t is equal to 0, the switch will become closed. So it's a transient case or switching case. Okay, so as the initially before the instant of 0 time, the switch was open for a long time. From the negative infinity time axis, the switch was open up to the present moment. Now I am going to close the switch. So what will be the initial current? As the switch is open up to the moment from a long back, then we can definitely say I0 will be 0. Okay. So when switch is open, this is the condition. For time less than 0, this is an open circuit. So I0 minus is equal to 0, I0 is equal to 0, I0 plus is equal to 0. These three are very close instants. As I0 minus is equal to 0, you should assume that just at the time of closing I0, then also the current should be 0. And if the instant just after that I0 plus, that will be also having same value. So we know that before the closing of switch I0 minus, this is I0 minus, just before closing of switch, we know that current was 0. So you should assume that I0 should be 0 and I0 plus should be 0. I0 plus means the switch will not break like this. This is the same instant I am showing. But after I0 plus, after 1 or 2 seconds, the transient behavior, not 1 or 2 seconds, it will be in microseconds, the transient behavior starts. So for that, we have to draw the present circuit condition and we have to apply KVL. So after t is equal to 0 or t greater than 0, this is the circuit condition because switch is closed. Now switch is closed. So the circuit is having a resistance and inductance. Those are connected in series with a battery. Okay. So now we can apply KVL in the figure. For applying KVL, we know that this is the plus and minus polarity of the battery. So current will come out from the plus polarity like this. So it is entering at this polarity of this side of resistance. So I have to mark plus at this side and the current will be going like this in clockwise direction and it will be entering at this terminal of inductor. So I marked plus at this terminal and leaving at this terminal, so minus at this terminal, and the circuit will get completed here. So what will be the KVL equation? If you are tracing in a clockwise loop, you will see the E first. Which terminal? If you are moving in clockwise fashion, which terminal you will see? Minus E plus current into resistance Ri plus voltage of this inductor. What is the voltage of this inductor? Plus L di by dt, that is equal to 0. So L di by dt plus Ri, that is equal to E. This is the basic KVL equation of this circuit. Now please check what is the coefficient of the basic variable in left side, that is I. So coefficient of I is equal to R by L. That R by L is known as integrating factor of the equation. So multiply both sides with this integrating factor. R by L is the coefficient of I. We have to develop integrating factor from that coefficient of I, and integrating factor is equal to e raised to that R by L into t. So that is the integrating factor. R by L is not the integrating factor. You have to take e raised to that R by L into t. That is the integrating factor. So please multiply both sides with this integrating factor. Okay, this will be very simple. First term will become e raised to R by L t di by dt plus e raised to R by L t R by L into I is equal to, on right side, there previously it was E by L only. Now it will become E by L into e raised to r by l t. So, I know you may have many methods for solving this, but if you want to solve very easily, if you want to solve it very easily, you have to apply the product rule of differentiation. If you are doing differentiation of d by dt of two variables x into y or x1 into x2 like this, please consider this will be the simplest method. Please consider this case. If you have to take differential of e raised to r by l t into I with respect to time, what will be the differential? What is the product rule? First, you have to take the differential of, you have to make the first term constant and you have to find the differential of second, plus make the second term constant and then differentiate the first term. So, you will get the same thing. If you are determining the differential of this term, the answer will be this. See this, e raised to r by l t, it is the first term, into di by dt, it is the differential of second term, plus e raised to r by l t into r by l. What is this? It is just the differential of e raised to r by l t, that is e raised to r by l t into r by l into I. In this one, second term is made as constant. So, instead of the left hand side, you can easily substitute d by dt of e raised to r by l t into I. So, our equation will become d by dt into e raised to r by l t into I is equal to e by l e raised to r by l t. And now I am cross multiplying this dt into this side. So, you will get d of e raised to r by l t, it is just plus, it's not needed, r by l t into I, that is equal to e by l into e raised to r by l t into dt. Now, you can do the integration on both sides without having any limits. If you are doing so, you have to take a constant of integration, or it is the anti-differential concept. Okay, I hope you know it. So, if you are integrating both sides, you will get e raised to r by l t into I, that is equal to, if you are integrating this one, you will get this e by l is a constant and then e raised to this term will be like this only. Then you have to divide the whole term by r by l. So, as it is dividing, it will become l by r. So, l by r into e by l e raised to plus r by l t plus a. A is the constant of integration. This is the case, e raised to r by l t into I is equal to e by r e raised to r by l t plus a. Now, for simplifying it, divide both sides by e raised to r by l t. Then you will get I. I is nothing but it is a function of time. I of t is equal to e by r, because that this term will get cancelled. So, I of t is equal to e by r plus a into, you are dividing by e raised to r by l t. So, it will become e raised to minus r by l t. This is the final current equation. And you already know that to find a, what you have to do? We have to apply the knowledge about initial condition. What was the initial condition? Initially switch was open, I0 was 0. So, you please put t is equal to 0 in the obtained current equation. And that value will be, you know that initial current is equal to 0. So, 0 is equal to e by r plus a into e raised to minus r by l into t. This t should be also substituted by 0. So, what happened? E raised to minus 0, that is equal to, e raised to minus 0 is equal to 1. So, you will get e by r plus a is equal to initial current, that is equal to 0. So, a is equal to minus e by r. So, what is the final equation of I of t? I of t is equal to E by R minus E by R, because you are substituting for A. I of t is equal to E by R, this was actually A. Now you are substituting it minus E by R into e raised to minus R by L t. Okay. Now you can easily do one thing. You can take E by R outside. So I of t will become E by R into 1 minus e raised to minus R by L t. Okay, now we can just check whether what happened when t is equal to 0. You already know that when t was 0, the switch was open and its response was 0. But you are just cross-checking whether your answer is right or wrong. So when you put t is equal to 0, I of 0 is equal to E by R into 1 minus e raised to minus 0. The total term will become 1 minus 1, that is 0. So I of 0 is equal to 0. So your initial condition is verified. Now when t is equal to infinity, t is equal to infinity means it is after a long time. Long time means actually you are doing some switching. So some disturbance may happen. This disturbance may persist for some time, some 5 or 10 time constant. Actually, we already familiar with time constant in the last lecture. If you are having more doubts or you didn't watch the last lecture, please refer that before coming to this concept. So if time constant, after 5 or 6 time constant, this value will reach to its final value. In last class we checked that at the first time constant it was reaching 63.3%. After 5 time constant it was reaching very close to 100%. Like that, we know that we will get some some final value, and that final value will be after some particular time. Generally, we don't know when it will reach the final value, but we know that at infinite time, after a long time or at infinite time, anyhow the system will reach its final value slowly. Anyhow the system, this is the time axis and this is the current axis. Initial value is 0. It will be go like this. Somehow after some time it will reach its final value. So if you don't know after what time it will reach at what value, blindly put t is equal to infinity. Infinity means it is a time after very long interval. So definitely the system will reach its final value or steady value. That final value is known as steady value. And this is not steady value because it is having some disturbance and it is going towards some final value. After a long time it will reach the steady value or final value. For getting final value, you have to substitute t is equal to infinity at the current equation. So I of infinity is equal to E by R into 1 minus e raised to minus R by L t into infinity. So the total term will become minus infinity here, minus infinity. So minus e raised to minus infinity means 0. So the I of infinity is equal to E by R. So the final steady state value of the system is E by R. So what you got understood? Its final value doesn't depends on magnitude of final value, doesn't depends on inductor. It is just depending on E and R. So E by R is the steady state value. But you should think, what is the dependence of L? L depends on time constant. When it reached the final value, or what is the speed of moving towards final value, such things are depending on L. Okay. Okay, I am sorry because up to this moment everything is right. But in last class we didn't discuss about the time constant. Now only we are going to discussing about time constant. So I am sorry. So anyhow, now you got that when I is 0, the current value, initial current value was 0. When t is infinity, I of infinity is E by R, that is the final steady state value. So I am asking you when the response will reach E by R, or when the response will reach final value. Actually what was the mistake is, I was just thinking that in last class I delivered all these concepts also. That's why, sorry. So time constant was not introduced to you up to the moment. So So this is the moment where you are going to learn time constant. So no problem. Come on. So time constant is nothing but for a RL circuit, time constant is equal to L by R. Please understand this concept. L by R is equal to time constant. What is time constant? So because we don't know its initial value is 0 and final value is some E by R. How it will travel? There is lot of options. For example, this is 0 and this is E by R. It can travel like this or like this, like this. The current wave can travel in many ways. You can see here. This is E by R, the final value, and this is the time 0 instant. It can travel like this or it can travel like this, or it can travel like this also. Anyhow, it has to reach final value at some time. But when it will reach final value, or when it will reach 50% of final value, when it will reach 90% of final value, such things are now unknown for you. For discussing about such factors or such condition or speed of response means how it will reach final value, when it will reach final value, when it will reach 50% of final value. So you see here. Okay, we will discuss. Anyhow, for that we are introducing a term time constant, that is nothing but L by R. So what was our basic equation? I of t is equal to E by R into 1 minus e raised to minus R by L into t. Okay. Now we are assuming various values for t. When t is equal to 0 and t is equal to infinity, we got initial value and final value. Now I am assuming when t is equal to L by R, what happens? T is equal to L by R means in this equation, here you have to supply t instead of t, L by R. So L by R and R by L will get cancels. So you are going to substitute t is equal to L by R means you are assuming t is equal to 1 time constant. For each circuit, the value of that L by R may be different. For example, in your circuit, you are taking L is equal to 10 and R is equal to 1. What is L by R time constant? L is equal to 10 and R is equal to 1. Its time constant will be 10 seconds. If L is equal to 20 and R is equal to 1, time constant for that circuit is 20 seconds. Like that, time constant may vary in all circuits based on the L and R value. But I am saying L by R is equal to time constant and you are assuming t is equal to 1 time constant means for the particular example, which is the example, L is equal to 10 and R is equal to 1, you are taking t is equal to 1 time constant means it is you are commenting about the case when t is equal to 10 seconds. T is equal to 2 time constant means you have to take t is equal to 2 into 10, 20 seconds. T is equal to 5 time constant means you have to take t is equal to 5 into 10, 50 seconds, like that. So in this case, we don't have any specific value for R and L. So you are taking t, time constant is equal to L by R is equal to t when t is equal to tau. Tau means time constant, 1 time constant. You have to substitute here instead of t, L by R. So this L by R and the L by R get cancels. So it will become E by R into 1 minus e raised to minus 1. This value will give 0.6322 E by R. Or if you are expressing in percentage, it is 63.2% of final value E by R. So what is the thing you got understood? In such a circuit, if you are assuming time is equal to t is equal to 1 time constant or t is equal to tau or t is equal to L by R, whatever may be the L by R value, you will get some particular value for tau, that's understood. But for that value, you will get your output will reach us 50% of final value. If this is the E by R is the final value, its 50% means it will be lying here somewhere. So it will reach us this 50%. Now when what was the answer you obtained? 63.2% of final value. So suppose this is an example where L is equal to 10 and R is equal to 1. Time constant will be 10 seconds. For 10 seconds, its output will reach 63.2% like this. This will be 10 seconds. But now I don't know what is the second. That's why we are taking T is equal to tau. Tau is equal to L by R. That value is standard value L and R. I don't know the specific numerical values for that. Anyhow, for that condition, its speed will be 63. Its output will reach 63.2% of final value E by R. Now substitute T is equal to 5 time constant. Suppose for our example that I considered, if L is equal to 10 and R is equal to 1, time constant means 10 by 1, 10 seconds. So 5 time constant means T is equal to 5 into 10, 50 seconds. So this is the, suppose this is the 10 second, this will be the 50 second. Then if you want to find the particular percentage of output E by R, or what is the present value of present value you obtain, for that you have to substitute T is equal to 5 tau in the standard equation. What was the standard equation? I of T is equal to E by R into 1 minus E raised to minus R by L into T. Initially it was T. Now you are substituting it. Instead of T, you are giving it 5 tau or 5 into L by R. So L by R and R by L will get cancels. The equation will become E by R into 1 minus E raised to minus 5. That is 0.99. So what is the case? When you are observing for a time where time is equal to 5 into tau, then its output current will reaches 99% of its final value. You can see the orange line is equal to 99% of the final value. So the final value will be just above it. I didn't mention the E by R value. I mentioned 99% of E by R value. So the 100% E by R will be just above that. So in any RL circuit, if you give a time of 5 tau, then definitely its output value will become equal to 99% of final value of current. But how you get what is the exact value of that time? Then you have to substitute for tau. Tau is equal to L by R. L and R are unknown up to this moment. But I took one example. If L is equal to 10 and R is equal to 1, then time constant will be 10 by 1, 10 seconds. So in this case, if you are taking time is equal to 5 tau, you have to take 5 into 10, 50 seconds, like that. Based on that L by R value, the curve shape will be different. Okay. Now it is response of inductor voltage. Up to the moment we were discussing about response of inductor current. Now we want to discuss about the response of inductor voltage. Now please see the current equation. There is a small adaptation. I of t is equal to E by R into 1 minus E raised to, what was previously? Previously it was R by L into T. Now I substituted R by L is equal to 1 by tau. That's why the equation became I of t is equal to E by R into 1 minus E raised to minus T by tau, and tau is equal to L by R. Now voltage VL of t is equal to L di by dt. Voltage VL of t is equal to L di by dt. So already we got the expression for current. Now for getting the voltage, we have to take differential of that current with respect to t. So L di by dt is equal to L into d by dt of that equation. So in this case, 1 is a constant. So the differential of minus e raised to minus t by tau is equal to into e by r, that is equal to e by r is a constant also, minus e into e raised to minus t by tau. Anyhow, e by r is a constant, and you will get minus e raised to minus t by tau divided by, as it is differential, into 1 by tau. 1 by tau means, yeah, okay, if you are taking e by r outside, it will become L e by r into d by dt of minus e raised to minus t by tau. So you will get e L by r into minus 1 by tau into e raised to minus t by tau. So if you are cancelling all these things, you will get finally e into e raised to minus t by tau. So VLT, or the expression for voltage, is equal to E into e raised to minus t by tau. Now we are going to sketch the waveform of E. Anyhow, in all these things, you are getting a CARA based on some exponential relation, because in all this equation there is an E term. In the current also, you can see it will be, this is the current equation, e raised to e by r into 1 minus e raised to means exponential term. So for all these CARA, you will get a positive exponential or negative exponential relation in the waveform. So now in the voltage equation also, you can substitute what happens when t is equal to 0 and what happens when t is equal to infinity. When t is equal to 0, VL of t is equal to e into e raised to 0, that is e. So this is the case. In current, when time is equal to 0, it was also 0. But in voltage, when t is equal to 0, initially it is on some high value, that is a value is e. When t is equal to infinity, exponentially it is coming towards the 0 value. VL of infinity, you will get e raised to minus infinity, that is equal to 0. So initially the value is e, and finally the value will be 0. So it is exponentially decaying, not increasing. It is exponentially decaying towards 0. So at t is equal to 0, what happened? At t is equal to 0, initially the switch was open. Okay, initially the switch was open, and at t is equal to 0, switch got closed, and you are getting a high voltage E, that is a sudden jump, and then you can see the current value is, the voltage value is decaying in step by step exponentially. So current through an inductor cannot have a sudden jump. You can check here. Sorry. Okay, you can check here. Initially, this was the current before switch is open. Before the switch is closed at t is equal to 0, this was the current. At t is equal to switch is closed, and current is slowly increasing. No sudden jump happens in the current waveform. But in voltage waveform, you can see the voltage was 0 initially, and when switch is closed, suddenly the voltage is jumping. Voltage across the inductor is jumping towards a high value E, and then it is exponentially decaying to 0. So in the current waveform of an inductor, it will not have any sudden jump. But in the case of voltage waveform, it may have sudden jumps. That is the conclusion we are getting it. And the shapes, if you are plotting both the shape in a single figure, what happens? If this is the voltage waveform and you want to plot the current also in the same figure, you have to start from this point, and current will be like this. So you can plot both in the same figure also. Anyhow, one is exponentially increasing and other one is exponentially decaying. So the concept should be very clear for you. And this is the one more small thing related to this section. So, if you want to store energy in an inductor, store energy means equation of energy is equal to E is equal to half Li square. So, we may need some special circuit to pump current because the I value is very important. If current is exponentially increasing or exponentially decreasing, after reaching the particular value, we have some mechanism to keep that value constant. Then only we can say that energy is stored. So, for such a discussion, we need some more arrangement in the circuit. You can see at t is equal to 0, what happened? You can just see the figure. At t is equal to 0, we will move the switch. Switch is connected at the directly to the inductor. At t is equal to 0, we will move the switch to position A. So, this is the circuit, a RL circuit directly connected to a voltage. No need to discuss more because this was the discussion in the total class. So, we know that the current will start from 0 and finally it will reach a value E by R. Okay. So, after sufficient long time, the current will become approximately equal to E by R. In the last example, we know that when it will become 99% of E by R. What was the condition? When t is equal to, when time becomes 5 time constant, 5 tau, anyhow the current will become 99% of its final value. So, please see this. If this is the 100%, the current will become 99% for some t is equal to 5 tau. It will be here somewhere. So, now after that time, it is almost reached 99%. Now, no need to wait for a long time and wait when it will reach 100%. It is not needed. Anyhow, it is reached 99%. It is satisfactory. Now, you can move the switch to position B. What is, sorry. What is there in position B? This is position B. So, you are moving the switch into position B means an inductor with a permanent short circuit. This is the circuit. E by R is the circuit is there. So, E by R was the current, or it is approximately equal to E by R. That was the current initially flowing through the inductor, and now you move to another position where a permanent short circuit is there. But still, the direction of current in the inductor will be same because that is the basic property of inductor. It will not operate. It will not permit sudden change in current, and we should have some short circuit path to maintain the flow of current in the same direction. So, E by R is the current value. This value will remains constant because now you are providing a short circuit path and no resistor is there. In that circuit, there is no resistor, then energy will not get dissipated. That value will be constant for long time. So, that particular value is equal to E is equal to half Li square. So, why you connected the switch with the particular inductor only? Then only you can avoid the presence of resistance. After the current in the inductor reaches a maximum value. You can see after the 5 time constant, the value of inductor is very the value of current in the inductor is very close to the final value. What was the final value? E by R. E by R. Is it clear? And now you move the switch to position B. Now no resistor is there. It is a pure inductor is connected with a circuit, short circuit condition. So you can ensure that the inductor is stored with some energy E by R. Now let me ask one question. What happens if resistor is not there initially? If resistor is not there initially, because in this circuit, if resistor is not here and all the remaining conditions are same, what happens? Because I already told you resistor is a bad thing now. It is wasting, that will dissipate the energy, loss will happen, but the inductor will not make any loss. Then how you kept that inductor? What is the advantage of keeping that inductor initially? That is the flaw of my entire delivery. In first class I told you that, in lecture 15 I told you that if you connecting a inductor directly to DC without having resistance, what happens? Its current will not get its current will not go to a final value like this. That current will be shooting towards infinity. It will be ramping with a constant slope of R by L. That is the case. Now it will not happen. Now anyhow, due to the presence of resistor, it will follow a exponential trajectory and finally reaches a steady state value. Then only you are removing the resistance. Then only you are moving the switch to position B. So the resistance is also very important. On the charging state, then you are removing the resistor. So this is the case. So anyhow, this is a very important lecture, lecture 15 and lecture 16, because I am arranged these lectures in my own passion, and not only my own passion, I have referred some NPTEL lectures on also for arranging this portion, because if I am not mentioning about the concept like this, why what happened, pure inductor is there, if such things are not mentioned, if I am directly coming and just drawing a RL circuit, just closing switch, obtain its final condition, then only you can use that in your life, in your engineering life. For making this knowledge meaningful, such a overall idea is needed in this topic. So if you are having any more doubts, you can refer NPTEL videos also. I will give the link of that video also for understanding more concepts about this video. Anyhow, this is somewhat needed. In the next class, we will discuss about pure capacitor, and then we will go to the RC circuit, like that. So anyhow, I hope you enjoyed this session. Thank you for watching. We'll meet in the next class.